All right. Excuse me. Good morning, folks. Let's go ahead and let me get started here. And I'd like to try to get through and at least talk about the first set of titrations. So I want to try to get through titrations of strong acid, excuse me, and strong bases today, so that tomorrow we can try to continue on with the titration of weak acid. And it started the titration of weak acid. I'm sorry, weak acid, strong base, and then try to finish up with weak base, strong acid titrations, and we'll talk about that. Okay. All right. So let's go ahead then, and I'm going to go ahead and get started. And let's take a look at where we left off with yesterday. We were talking about buffering capacity, and we let me go ahead and share this screen here with you really quickly. We were talking about buffering capacity, and we were talking about we were trying to uh, we were working through this problem here. I wanted us to work this problem so that we can see then what goes into determining what a buffer being either a good buffer or a bad buffer. That means having a good buffering capacity or not having a good buffering capacity. So remember, we defined buffering capacity yesterday then as the ability of a particular buffer to resist a change in its pH. So a buffer with a large buffering capacity will have a better a chance that will be better at resisting any changes to its pH. Okay, whereas a buffer with a low buffering capacity will see greater changes in its pH. Okay, so we talked about that yesterday. I introduced that to you, and I wanted then to work through this problem here for you and get you to see then how we can have this. So we have two buffering solutions here, okay, and both of these are acid buffering solutions. So let me go ahead and I'm going to open up a whiteboard here so I have a little bit more room to work this problem out for you. Okay, so let me go ahead then and let's go ahead and let me share that with you. Let's see if that works. Okay, and let's go ahead and let's take a look at the two buffers that we have here. So both of these are both acid buffers, and they're made up of the same components. Both of these are acidic acid buffers, okay, which means that both of these are made up of acidic acid. So let's go ahead and write this one over here, C2H3O2, and its conjugate base, which is the acetate ion, C2H3O2 minus. And the concentration of our first buffer here is going to be a 5 molar solution of acidic acid mixed with a 5 molar solution a 5 molar solution of the acetate ion. Okay, so this is our first buffer, and this is our base buffer, and I'll call this base solution A. So I'm sorry, base buffer, acid buffer A. So this is our first buffer here. So this is acid buffer A. All right. All right. Then we're going to compare this. So what I'm going to do is then right next to it, I'm going to add then the second buffering solution. Okay. So the second buffering solution is also a acidic acid. I'm sorry, H. Sorry. I'm going to do this really quickly. I'm not done with this yet. So it's be H. Sorry. HC2, H3O2, and the acetate anion again. Okay. This time the key difference then is the amount. So we have then 0.05 molar of acidic acid, 0.05 molar of the acetate. Okay. So this is going to be our acid buffer B. So this is acid buffer B. Okay, so two different buffers, okay, two different buffering solutions made up of the same components. So we have acidic acid, acetate buffer here. All right, so what we're going to do then is let's compare this. So what we're going to do is we're adding hydrochloric acid to both of these. Okay? So before we do that, though, we need to figure out what the initial pH is of each one of these solutions here. Okay, now my hope, and I asked you this yesterday, and we didn't quite get a consensus answer, but I hope that by the end of the work now, you're going to see then that both of these should have exactly the same pH. And how can we do this? Let's go ahead then and let's calculate for the initial pH. Then let's go ahead and do this. The initial pH okay, for both of these buffers here. And you can see that. So the initial pH, then we're going to use the Henderson-Hasselbalch equation because, let's go ahead and write this down, then the Ka, and we use the K, but same for both of these. It's going to be 1.8 times 10 to the minus 5. That's the Ka for both both of these solutions. They're both acidic acids, so that's going to be our Ka that we're going to be using right there. Okay. So let me go ahead and indicate. Oh, sorry. Let me go ahead and write that in there really quickly. So that's our Ka right there. So keep that in mind. This Ka is the same for both these. Remember, with equilibrium constants, those will always be the same for a given acid. The concentrations may change and change the equilibrium position, but the equilibrium constant will be the same. Okay. All right, why do we need this? Because first of all, let's compare. And we want to do this to check to see if we can use the Henderson-Hasselbalch equation to get the pH. Okay, we want to do that for both. Okay. So the Ka here is 10 to the minus 5. The initial concentration here is 5. Obviously, for this solution here, for acid buffer A, we can use the Henderson-Hasselbalch equation in order to solve then for the pH. So let's go do that. So it's going to be pH is going to be equal to pKa, right? And then we're going to have then plus the log of base over acid. So it's going to be the acetate, C2H3O2 minus over HC2H3O2. So Henderson-Hasselbalch, it's going to be base over acid. Okay. All right, so let's go ahead then, and I'll let you take the negative log of this one, but I'm just going to plug it in for you. The negative log to get the pKa of 1.8 times 10 to the minus 5, then it's going to be 4.745. Okay, and therefore then we're going to take the log of 5 over 5. 5 molar over 5 molar. Okay. The log of 1 is going to be 0, so therefore the pH of this solution then is going to be 4.745. I hope you're able to see that. Okay, so this is 1. Log of 1 is going to be 0. This is 7.745. That's the initial pH of this solution. So buffer A has an initial pH of 4.75. That is before we add anything in there. Now, I'm going to go ahead and do this. I don't mean to insult your intelligence by doing this, but let's go ahead and let's calculate for the initial pH buffer acid buffer B. Okay, so let's go ahead and calculate for this initial pH here, just to see then, just so you can see then that there's no tricks to this. This is not magic, not smoke and mirrors. That I get the same pH here. But let's go ahead and use this. Okay, so can we use the Henderson-Hasselbalch equation? This is 10 to the minus 2. This is 10 to the minus 5. We are close. We are awful close. So it's within that range though. So this is 1,000 times bigger than what we have here. So 10 to the minus 2, 10 to the minus 5. It's going to be about 1,000 times bigger. So let's go ahead then and let's use the Henderson-Hasselbalch equation. So again, the 5% rule is going to work here. Okay, plus the log of base, conjugate base over acid, H3O2. So everything is exactly the same so far. The pKa should be exactly the same. So the Ka is exactly the same as well. So it's going to be 4.745. Okay, this time it's going to be the log of, and let's go to 0.050 molar over 0.050 molar, which is 1. Log of 1 is 0, and so therefore the pH of the second solution is exactly the same. And that's what we need to make sure we keep in mind. So the pH of both solutions that we start out with, they have to be the same. If they're not the same, we can't do this comparison. We cannot compare and answer the question about buffering capacity. So that you got to make sure you keep in mind as we work through this. Okay. All right. So keep that in mind as we work through this, because now what we're doing then is we're going to add to both solutions here an equal amount of acid. Okay, so we were told that we're going to add that we're going to bubble in 0.10 moles of gases, hydrochloric acid, and 1 liter. So essentially then, what we're going to be doing then is we're going to add a concentration of hydrogen ion, because hydrochloric acid is strong acid. That's going to be equal to 0.010 molar. So to both solutions then, we're going to add this. So hopefully you recognize this also, that when you add in this strong acid here, it's going to react with the base side, okay, the base component of the buffer. Okay, so We're going to add 0.010 molar to both of these, okay? Which means that as we do so, and let's make sure we keep reviewing this, this is going to lower the amount of the base and increase the amount of the acid. So we're going to see an increase in the amount of the acid and decrease in the amount of base for both of these here, for both of them. Okay? So that's what we're going to see when we work this out. Okay? So with that said, we will work out, we're going to do the stoichiometry first. We're going to do the stoichiometry first. And remember, the stoichiometry this time is going to involve then the reaction between hydrogen. Okay, so let's go ahead and write this down. It's going to be the reaction between hydrogen ion, okay, the acetate anion, okay, to form for us then the acetic acid. Okay, so we're going to ignore everything else. We're just going to focus on that. Okay, all right, so let's go ahead and set up our table then. The initial concentrations of each one of these is then, it's going to be 0.010 molar of the hydrogen ion. We have then 5 molar solution of the acetate for our initial, for acid buffer A. Okay, all right, so that means then the initial moles, so let's go and write that down. The initial moles here in a 1 liter solution, it's going to be 0.010 moles of hydrogen, which is going to have 5 moles of acetate. And again, no acetic acid initially. Okay. All right, so now once the reaction runs, remember, we're adding this acid. The limiting reagent should always be the amount of acid that's added in. So that would run out first. So this is our limiting reagent. So we end up with 0 moles at the end. Okay. So we'll end up with 0.010 moles of the acetic acid. And then if we do the math here, then we end up with 4.99 moles of the acetate, okay, left over, which means then the final concentration, which is what we will need to find the new pH, is going to be then 0 molar for the hydrogen. Okay, this is going to be 4.99 molar. And again, the reason why we can do this is because we are assuming a 1 liter solution. So if we have a 1 liter solution, moles over liters gives us the molarity. And so we have then 0.010 molar of the acetic acid that forms. Okay. All right. Hopefully all that is pretty straightforward. Let's continue on then. Okay, and let's calculate. So that is, let's go ahead and do this. That was the first calculation. That was our stoichiometry. Okay, let's go ahead then and let's do the equilibrium. So we're done with the stoichiometry. Okay, now we got to go ahead and we now that we need the we have the values that we need, we can use the values that we obtained here in the stoichiometric calculation to do the equilibrium. Okay. Okay, so let's go ahead and calculate for the equilibrium. And again, we should be able to use the Henderson-Hasselbalch. Why? Because look at this. This is our pH here. I'm sorry. Let's go ahead and let's determine this in. All right. So we have then the equilibrium concentrations. Let's go ahead and do this here of acetate. Okay. So we drop from 0.5. I'm sorry, 5 down to 4.99. Okay. So that means that the concentration that we're going to use here for acetate now, the new concentration, the equilibrium concentration that we will use to determine then the new pH is going to be the, I'm sorry, the initial concentration here. It's going to be 4.99 for acetate. Now remember, for the acetic acid, we expect it to go up. Okay, so that means we have to add that in. So we're going to have then 5.010 molar. So it's going to increase like we predicted here, and that's going to be our concentration. So this acid concentration here obviously is still a whole lot bigger than the Ka. We can assume the 5% rule. Let's use the Henderson-Hasselbalch equation to find the new pH. Okay, so the pH says it's going to be equal to pKa plus log the base over acid. So C2H3O2 minus, okay, all over the concentration of the acetic acid, HC2. H3O2. Okay, let's go ahead and plug in our numbers. pKa still has to be the same. That doesn't change. That never changes. That cannot change regardless of what we add into this. That pKa is still going to be the same. It's a constant. Okay, that's 4.745 plus the log of, and let's go ahead and plug this in then. It's going to be 4.99 molar over 5.010 molar. If you plug that in, I get an answer here. So I'm going to leave it up to you to kind of confirm this for me. I get a pH now of 4.743. 4.743, yeah. 0.743. That is the new pH. After we've added in the 0.01 molar, after we've added in the acid, that is the new pH. Okay, that is the new pH of this acid buffer A. Okay, so if we take a look at the difference in that is the change in the pH. If we take a look at the change in the pH, and let's go and do this really quickly. Okay, the change in the pH for the acid buffer A. Okay. Okay. And so we're going to take then final initial minus final. Then let's go and do this. Okay, so we have then 4.745 minus 4.743. Let me go ahead and plug that in really quickly, and let's compare this. So that's going to be the change of pH there. Let's see, 4.745 minus 4.743. I get a 0.002 change. 0.002. That's the change in the pH that occurs when we're using this buffering system right here. We have a 5 molar sample. We've mixed 5 molar. We have a 5 molar concentrated solution of acidic acid with a 5 molar concentrated solution of acetate. Okay, so now that's the pH change there for buffer A. Let's compare then the pH change for buffer B. Let's go ahead and do the same thing, and I think we can go through the this second part here a little bit more quickly, because we're going to be doing carrying out the exact same calculation again. So we're going to do the stoichiometry first. Stoichiometry first. Okay. All right, so with the stoichiometry here, it's going to be, again, the process is going to be exactly the same. So I'm going to, again, go through this fairly quickly. I know that it's going to be somewhat tedious, but I want to go through this slowly enough for those of you so that everyone can follow what's going on here. Okay. All right. This time, the initial concentration of acid will still be the same here. This can be 0.010 molar. This time, though, the acetate is 0.050. So 0.050 molar. And we have no acidic acid here. Okay, so the number of moles, the initial moles, then is in a 1 liter solution, then we expect that we have 0.010 moles of hydrogen ion, 0.050 moles of acetate, and no acidic acid initially. Okay, then after the reaction is done, this is still, again, this is a hydrogen. The amount of acid still has to be the limiting reagent. We can't have more of it. So if we take a look at this here, this will run out first, okay? And therefore, then we will form 0.010 moles of the acidic acid. But if you notice here, then the change in the acetate then, okay, is going to be 0.040 moles. Okay. All right. And then finally, the final concentration, which is what we need to go on to the second step, then it's going to be 0 molar here for the hydrogen ion. This is going to be 0.040 molar solution forming of the acetate. And then we have then 0.010 molar of the acidic acid. Okay. All right, so now that we have those numbers, let's go ahead then, let's go on to the second calculation, okay, which is going to, involve then the new equilibrium. So we're going to calculate for the new equilibrium here. Okay, the new equilibrium here, and the second step here is the equilibrium step. Okay. Now, with the second step here, let's go ahead and let's figure out what we have. Okay. All right, so the amount of, we expect then the amount of acetate to go down, and we see it go down here. So the concentration of acetate, C2H3O2, is going to be now 0.040 molar. It started out at 0.050, it dropped down to 0.040. 0.40. So we expected that to happen. Okay. The concentration then of the acetate, C2H3O2, we expect to go up. Okay, so we're going to add that in. So we have then 0.060 molar concentration. So hopefully you got that. Okay. All right. So will the Henderson-Hasselbalch equation still work? Yeah, because this is still 10 to the minus 2. This is 10 to the minus 5. So we're still at a factor of about 1,000 times greater that this concentration for the initial the concentration for acetic acid. So let's go ahead then. We can use the Henderson-Hasselbalch equation to solve for. Okay, so let's go ahead and let's plug that in. We have acetate, so it's going to be base over acid. Okay. All right, so let's go ahead and plug in our numbers. pKa then again should not change. So it's going to be 4.745 plus the log. Whoops, sorry, the log of the acid anion here is going to be 0.040 molar over 0.060 molar. Okay, and so if you do the math there, we get a pH here then that is going to be 4.569. That's going to be the new pH now that we've that's the new pH that we'll have at equilibrium after we finish adding in that 0.01 molar solution of hydrochloric acid to this acid buffer B. Okay. So let's go ahead and let's do that. This same analysis here. Let's take a look at the change in the pH. Okay. The change in the pH then for the second solution then is going to be 4.745 minus 4.569. Okay, so the change in pH here that I get then is 0.176, which is still not a very big number. This is still not a very big number, but if you look at this, then that's a whole lot bigger than buffer B, buffer A. So what we see happening here then is that acid buffer A is more resistant to its change in its pH. It undergoes only a 2,000th of a change in its pH. Here we have a almost a 2/10 of a change in its pH. So acid buffer B, buffer solution B, which is a more dilute solution buffer, okay, sees a greater change in its pH. What does that mean? That means that it's more susceptible to a change upon addition of an acid or base. That, with that said, then what I think what you should recognize here then is which one of these then is more resistant to changes to its pH? The more concentrated solution. We have a whole lot more of both of these here. And so what we can do then, we can say this, okay, that buffering capacity, okay, let's go ahead and summarize here. Buffering capacity increases with increasing concentrations of buffering components. And that is what we see. Okay, and that is what we observe in this particular problem. And this is what I wanted, this is why I wanted us to work through this problem, because we see then that the buffering capacity is directly dependent upon how much of the buffering components we have. If we have more of the buffering components, it's going to be more resistant to changes in its pH. And that's exactly what we see happen right here. So the buffering capacity is going to be, dependent upon these initial concentrations here, or these concentrations here of the buffering components, the components of the buffering of the buffer itself. Okay? All right. I know we spent a lot of time in this problem, folks, but buffering capacity is a very important concept for you to kind of wrap your mind around, because it is something that we have to consider in practice. I mean, in class here, we talk about the theory, but when you have to carry this into lab, or when you are working out in a lab and we're working industry, and you're asked to create a buffer, okay, and use that buffer to run your reaction, or use that buffer to transport a particular compound that you created. Okay? You got to be able to work through this calculation fairly easily and be able to determine then what buffer is going to offer you the most resistant solution to any changes in its pH. Okay, so there's a lot of practical applications to what we do here, and that's why I think we spent a lot of time on this. And so buffering capacity is a very important concept that does come up quite a bit in chemistry in general. Okay, and like I said, we already saw then. I already introduced you when I introduced you just to buffers. We saw then that buffers are essential components of organisms, of living beings. Okay, we have buffers that we can resist any changes to our pH. Okay? All right. So please make sure you come by and you see me. Your homework kind of went over this, so please come by and see me if you have any questions about buffering capacity, and let me know. Okay, so I'll be available today after school. So come by after school today, and then we'll talk about buffering capacity. But let's go ahead then and let's review. And let me just go ahead and close this here. Sorry, let me save this really quickly. Okay, clear this out. All right, so let me go ahead and let's review them. Okay, now that we had a chance to work through that problem, okay, the buffering capacity then is going to be dependent upon the ratio of the acid, the base, and the acid. So the ratio of the components. That's what we have, the ratio of the components of this. So if we have a large amount of each one of those, we have a greater buffering capacity. Okay, and so that's what we have right here. And let me go ahead and just write it. Let me go ahead and clearly show this to you. Okay, so it depends on the buffering capacity. Depends primarily upon how much of the components we have. Okay, so the more we have of each one of those, the greater buffering capacity we have. Okay, all right. And with that said, then hopefully you got that. What I want to point out to you then is that the pH now, the pH of the buffer, so buffering capacity is dependent upon the amount of each one of those components that we have. The pH then is going to be determined by the ratio. Okay, whatever the ratio ends up being here, and we saw that, okay, whatever the ratio ends up being between the acid and its conjugate base, okay, is going to determine then the pH, because we plug that into the Henderson-Hasselbalch equation. We see that occurring right there. Okay, all right. So with that said, then when we talk about optimal buffering, for an optimal buffer, a buffer that is the best buffer then should have a high buffering capacity. Okay, and that's going to give us the most resistant change. Now, also, the ideal buffer then has to fall in line with the pH range that you are looking for. Okay, so if you're looking to maintain a certain pH, you got to choose a buffer that will allow you to keep that particular pH as well. Okay, so we'll talk about that in just a moment. Okay, so and then finally, the last thing we want to point out then is you have to have a whole lot of the components of the buffer, but the closer that ratio is to 1. Okay, that will allow then the pH to be fairly well maintained. Okay, so an ideal buffer, the optimal buffer should have a high buffering capacity, a whole lot of the components of the buffer, and that the components of the buffer should almost be equal to one another. Okay, the closer you can get to that, the better the buffering is going to be. Okay, so the less the change will occur with the pH with the addition of an acid or a base. So that's what you want to make sure you do. So when you're picking a buffer, and this is fine because you can actually mix all this together. You can mix as much as you need or mix as little as you need, but you can control that ratio. So that's why buffers end up being really, they sound complex to make to work with, but they are fairly easy to make. Okay? The issue then is making sure that you pick the right buffer. Okay? All right. So how do we choose the right buffer then? Okay? What do we do? All right, so the idea then is that if the ratio here, and let me go ahead and clear this out here. So if the ratio of the components of the buffer is close to 1, and the reason why we want it close to 1 is this. Okay? We can use then the pKa to determine the range, the rough range of the pH range of the buffer itself. Okay, how does that work? Well, let's take a look at what we have here. Okay, so we know then that this is the Henderson-Hasselbalch equation. And let's start out with this. Okay? Now, if you notice here, if again, and this is what I was showing you in the 2 examples that I pointed out to you, if these two are exactly equal to one another, okay, that means that it's going to be the log of 1, which gives us then the pH is equal to pKa. As long as then, let's make sure we keep this in mind here, as long as we have then this is being true, if the pH is equal, if these two are close to 1, if these two are close to 1, then what we have then is the pH will equal the pKa. So that means that if we wanted to say then, and we'll do a problem like this in just a moment, if you wanted a buffer that it's going to fall in range with, let's say, the pH range inside our body around 7, we can go ahead then and look for an acid that has a pKa close to 7. Now we know what the Ka values were. Real quick, simple calculation to do that, and then we pick an acid then that's going to have a pH that's closest to 7, and then we go ahead and we mix the concentrations of the acid and its conjugate base so that we have a ratio that is real close to 1. If we do that, then the pH is going to be very close to the pKa here. And if we can get this exactly equal to 1, well, we're in good shape. Then the pH is exactly equal to pKa. Okay. Let's take a look at an example here of a problem that's going to ask us to do that. Okay, let's go ahead then. And let's look at this problem here. Okay, so real quick, go ahead and grab your book, you guys. So pause the video if you have to, but go ahead and grab your book. And you're going to have to look back to table 14.2 in chapter. So this is back to chapter 4, okay, and it's on page 658. And so what we want to do then is like exactly what I just told you. We have a list there of acids. Okay, so on table, so go ahead and grab your book. On table 14.2, we are given the Ka values. We're given the Ka values for all of these acids here. We want to find the acid then that will get us a pH that's closest to 7. Now remember, when we go about doing this, okay, we want to make sure we understand this first and foremost, that once we pick this, we still have to mix them together. That means then whatever the ratio is that we mix between the conjugate base and its at whatever acid we choose, okay, we're going to mix it together so that the ratio here is going to be roughly 1. That has to be the case. If this is not the case, then what we do next is not going to be any good. Okay, so then what we're going to do then is we're going to find then the pKa values, and let's just pick a few here. Okay, let's pick. I'm sorry. Let me go ahead and write the table in here. Let me draw the table really quickly. Sorry. Okay. Okay. Let's go ahead and let's identify the acid. Okay. Let's write down its Ka, and then we got to calculate real quickly for the pKa. Okay. So we're gonna do this, and let's. I'm just gonna pick a few here. Let's take a look at the bisulfate. That obviously is a conjugate. That's an F-steric compound. The Ka here is going to be 1.2 times 10 to the minus 2. Let's go ahead then and let's pick another one here. Let's do nitrous acid, HNO2. Its Ka value, let me go ahead and look at you. This is 4.0 times 10 to 4.0 times 10 to the, let's see, nitrous acid, 10 to the minus 4. That's just for the sake of argument. Let's pick acetic acid too, since we've been doing that, working with this quite a bit. Let's see if this will be a good acid to mix in for our buffer. Okay, and so acetic acid then is 1.8 times 10 to the minus 5. Okay, and then let's pick hypochlorous acid, HOCl, so hypochlorous acid. Okay. It has a Ka of 3.5 times 10 to the minus 8. Okay. And so you notice here we're slowly getting weaker and weaker acids. And let's just use the last one. Let's use phenol, okay, which is going to be HOC6H5, okay? And that it has a Ka of 1.6 times 10 to the minus 10. Okay, all right. What I'd like you to do is let's go ahead and let's pause. So go ahead and pause the video. And what I'd like you to do is find the pKa's for each one of these here. Okay, so I'm not going to ask you to write this down. We're just going to, I'm going to give you a little bit of time to find the pKa's, and I'm going to do the same thing here. So go ahead and pause the video, and I'm going to go ahead and I'm going to find the pKa. Well, let's just do this together. Let's just do this together. So we're going to do the negative log of each one of these here, and I know it's going to take a little bit of time, but let's go do this. I'm going to practice this together with you to the minus 2. 1.2 times 10 to the minus 2. I get the pKa here of 1.92. Let's do the next one. Negative log of 4.0. Sorry, to the minus 4. Okay. I get a pKa here of 3.40. Okay. Let's do acetic acid, negative log, whoops, sorry, negative log of 1.8 to the -5. I get here 4.74. Okay. Let's do hypochlorous acid. Hypochlorous acid right here. Oops, sorry. Let me go ahead and let me take that off. Okay. All right. So we have then negative log 3.5 to the -8. I get here 7.46. Okay. And then finally, let's do the last one. And I think you probably already figured out which one we have to choose here. 1.6 to the -10. I get here 9.80. All right. So those are the pKa's. Now, the question here is then which one of these which one of these acids can we choose? Can we use in our buffer that's going to get us a pH that's real close to 7? I hope you see that it's going to be this one right here. It's going to be then. Oh, sorry. Let me go ahead and get rid of this one. Right. Okay. Hopefully you see then that it's going to be this acid right here. Okay. Now, and I hope you see the reason why. Okay. Because the pKa here is the closest one that we have to 7 right there. And as long as then, if we mix the acid together, so we're going to make this particular buffer solution, we're going to take hypochlorous acid, HOCl, and we're going to combine it with its conjugate base. It's going to be the hypochlorite anion. Okay, we're going to combine it together, and we're going to make pretty darn sure that we get real close. And I'm just going to pick some arbitrary number here. That real close, the concentrations of each one of those is going to be real close to 1. Okay, and here again we can measure this out. So there is our buffer solution. If we make this buffer solution here, then we will get a pH that's real close. So the pH of this buffer solution is going to be right here, 7.46. So this would be the ideal buffer for us to use. Now, would we want to choose this one? The one thing that hopefully you can recognize here is we may not want to choose this one right quite yet. This is the components, but we may want to, if we want a better buffering capacity, increase the amount, increase the concentration of each one of these. Okay, and so that's what the use here is of what we would do then with the buffering capacity, and the reason why we want to make sure then that this ratio here is as close to 1 as possible. Okay? And it just helps us to choose the correct buffer, the best correct buffering solution. Okay, all right, very good. What we'll do tomorrow, and I'm out of time here. What we'll do tomorrow is then we're going to start titration. So please make sure you look at the buffering problems here, work through these, and come by and see me and get some extra help with it. But hopefully work through this. You have an idea. Hopefully at this point now you have an idea of what buffers are, how to deal with buffer calculations. And the importance of buffers, I know it's going to take some time for you guys. It's going to settle in. You're gonna have to wait until that time that you were in your physical chemistry class, or you're actually working in a research lab somewhere, and then you have to make these buffers. Hopefully you'll remember the calculations. You probably will. I have no doubt about that. But hopefully you'll remember that. Hey, Mr. N introduced that to me, and quietly thank me. But whatever. All right. Have a good rest of your day, you guys, and I will see you folks tomorrow. Okay, and please make sure you come by and get your questions answered. Okay, I'll see you tomorrow. Okay, bye.